In this presentation, we'll explore data privacy techniques and how to implement privacy controls in databases. Protecting sensitive information is crucial, and databases are often a primary target. So let's understand various methods to safeguard data effectively. Data privacy is not just a buzzword, it's a critical necessity in today's digital landscape. Unauthorized access to sensitive information is a key concern, as breaches can lead to identity theft, financial loss, and other harms. Regulatory compliance, such as with GDPR, CCPA, and HIPAA, mandates strict data protection measures. Failure to comply can result in hefty fines and legal repercussions. Data breaches can have a significant financial impact, including recovery costs, legal fees, and compensation to affected individuals. Maintaining user trust is essential for business success. Data privacy challenges in databases include balancing data utility versus privacy. Access controls need to be managed effectively to ensure only authorized personnel can view sensitive data. Data must be protected during transfers, whether within an organization or externally. Implementing privacy by design means integrating privacy measures into every stage of the database lifecycle. Here are the database privacy fundamentals. Data encryption protects data both at rest and in transit, rendering it unreadable to unauthorized users. Access control involves role-based permissions and authentication, ensuring that only authorized individuals can access specific data. Data masking hides sensitive information from unauthorized users while allowing them to work with realistic, but not real, data. Anonymization removes identifiable information from datasets, making it impossible to link the data back to specific individuals. Let's look at database encryption examples. First, we'll create a master key using a password. Then we create a certificate for data privacy. Then we create a symmetric key using AES 256 algorithm for encryption and encrypt it by the certificate we just created. This code shows how to use encrypted data. First, we'll open the symmetric key for decryption by the certificate. Then, we'll insert encrypted data into the customer's table. We encrypt the credit card information using encrypt by key function, which takes the data key and the actual credit card number as parameters. Now let's dive into implementing data masking in SQL. Dynamic data masking lets you hide sensitive data from non-privileged users. Here's how to create a table with masked columns. The create table statement creates a table called patients, with columns such as patient ID, first name, last name, social security number, and birth date. We're applying a mask to the first name, last name, and social security number columns. We can also manage mask permissions using the grant select statement on patients table to the nurse role. We grant unmasked permissions to the doctor role. An example query run by a nurse returns the patient ID, masked first name, masked last name, masked social security number, and the actual birth date. The example query run by the doctor returns all the actual patient information. Next, we will discuss data anonymization. Here's how to implement k-anonymity in SQL. First, let's look at some original patient data. This code creates a sample patient data table with the columns like patient ID, age, zip code, and disease. It also inserts some sample data into the table. Now, let's create an anonymized view with generalization to ensure k-anonymity. The anonymized view creates a view called anonymized patients, which selects the age range, zip region, and disease from the patient data table. Age ranges are created using a case statement, and only the first 3 digits of the zip code are shown. Here, k equals 2, meaning that each combination of attributes will appear at least twice in the dataset. Now let's explore role-based access control. Here's how to implement it in PostgreSQL. First, we'll create application roles for doctor, nurse, and receptionist. Then we'll create user accounts, for example, for Dr. Smith and Nurse Jones. Finally, we'll assign the users to the roles. Dr. Smith is assigned to the doctor role, and Nurse Jones is assigned to the nurse role. Now let's set some table permissions. Doctors can see and modify all data. Nurses can see patient data but can only update vital signs. These grants ensure that each role has appropriate access levels, limiting the risk of unauthorized data access. Let's go beyond basic controls. Differential privacy adds calibrated noise to query results to protect individual records, while maintaining statistical accuracy for aggregate analysis. Homomorphic encryption allows computations on encrypted data without decryption, enabling secure processing while preserving privacy. Federated learning trains algorithms across multiple devices or servers holding local data samples, without exchanging the data itself. Zero-knowledge proofs is a cryptographic method allowing one party to prove they know a value without revealing the value itself. Here are some best practices for implementing database privacy controls. Incorporate privacy controls from the beginning of database design, not as an afterthought. Combine multiple privacy techniques for comprehensive protection against different threats. Collect and retain only the data necessary for the intended purpose to reduce privacy risks. Implement comprehensive logging, and conduct regular privacy audits to ensure compliance. Train database administrators and developers on latest privacy techniques and regulations. Conduct assessments before implementing new database features or collecting new data types. Balancing data utility with privacy protection is an ongoing challenge that requires vigilance and adaptation. These practices will help you create a robust and privacy-conscious database environment. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.